Hi there, this is Jacob Nash, and this is lesson 2 for Calc 2 Quick Substitution Rule. So before we get started, do you remember how to do or how to calculate antiderivatives? So not that hard, but let's just put it on here to remember. So if we were calculating this, okay, all you have to do is the reverse power rule for this one. So what it means is you add 1 to the exponent. So this is a 3, now it's 4. This is 1, now it's a 2, sorry. This is nothing, pretty much x to the 0. It's just there's no x there, so we make there be an x there. If it's just a number, there ends up being an x. And then you have to always do plus c if there's no bounds. See, no numbers here, here. X, or sorry, C. Put a C there. Remember, it's because when you're doing the derivatives, there are things that are able to disappear. So how we're accounting for that when we're going back is the C. And it's supposed to be a capital C, by the way. Then you have to do something with the coefficient. So these two things have to multiply to equal there. So I do 4. You have to do what is there divided by the exponent you just chose. So 1 divided by 4, 1/4. 2 divided by 2, 1. And then, nothing for that. But that's the way that you have to do it. So you first add 1 to the exponent, then you do that coefficient divided by the new exponent you just chose to get your new coefficient. All right, what about right here? Add 1 to the exponent, 11, 1 divided by 11, 1/11th, plus c. Ooh, but we have something here. This actually is the answer, but this is the point of what this video is. We're going to remember how to use U-substitution if needed. How do we know we need to use U-substitution? Two possibilities. The first is way more common and very easy to see. The second, not as common, but we will look at an example when it happens. So, um, if a function's embedded within another one, so if I see something under a square root, if I see something in parentheses, if I see something after a sign, if I see something after a log, uh, then I might think that I'll need to use substitution because there's nothing else I can do. The second thing is something and its derivative are in the function. So that means I see something that we're trying to take um, the integral of, and then I also see the derivative of that thing. And it will make more sense why that's a reason in a second. And I really meant that. This is the first example, and this one happens to be we're using number 2 as the reason because if you notice, if you take the derivative of this, we get 2x plus 1. So that gives us a clue. We only know how to use this. We're going to learn other ways to solve these, but they're doing this on purpose, whoever makes the problem, because they're knowing that something's going to cancel out. Because we can't solve this the way it is. So here are the steps. First, pick a U. So there are only two. You always just think of the different possibilities. Eventually, you'll be able to get it right on the first try. But if you're like, at least I was when I started this, I remember thinking, oh, well, there's so many possibilities. There's never actually that many. Just try them, and if it doesn't work, just do a different one. So there's only two possibilities, 2x plus 1, x squared plus x plus 3. We just did the whole thing, set that as u. That would be really stupid because that's the same thing as just not doing anything. Do you get what I mean? The point of why we choose a u is to get something to cancel out. If we do the whole thing, that's the same thing as if we did nothing. So there's really only two possibilities. 2x plus 1, x squared plus x plus 3. So this is what we pick u as. So the next thing that we do is we create an equation with three things. We put a du over here, we put a dx over here, and then in the middle right here, we take the derivative of what u was. There you go, 2x plus 1. Review how to do that if you don't remember. Um, if you want to really know how we get to this, it's the fact that this, if we're taking a derivative of it, this is du dx, right? Or u prime, whichever you prefer. But du dx would be equivalent if we get this dx over here. du dx equals du dx. That's how we get that. If what I just said didn't make sense, doesn't matter. You just need to know, put a du here, put a dx here, do u prime here. Now we get dx by itself, so we do, oh, du divided by 2x plus 1. Now, this is already worked out, but we put it in here, so we rewrite this down here, 2x plus 1 divided by u. Now we put u because of this right here. We That's what u equals, so 2x plus 1 divided by u. Multiply it by, we have to replace this dx with this, so du, and that's the whole reason why we did this, because now, yay, those two things cancel out. If nothing was able to cancel out, you know you did the wrong u, and you might start over. Now we're just left with 1 over u du. And if you remember, the antiderivative of 1 over u equals ln of absolute value of u. If you didn't know that, maybe watch the video I made for Calculus 1 where I talked about the different ones you'll want to memorize, and this is one of them. 1 over u is ln absolute value u, and then plus c. Remember this absolute value. That's very important. They want you to forget it. Then I just replaced the u with this. And there's supposed to be a c there. I don't know where it went, but we still need a plus c there. And that's your answer. Since there's no bounds, we can't actually solve it. But if there are bounds, you need to remember how to change them. And there's a crucial mistake that people make. So keep an eye on that, out for that when I'm saying this. So let's do this. Same thing. We'll pick u. There's only three possibilities, ln x squared, or 2x. The answer ends up being ln x. Once again, if you pick the wrong thing, you go back and do a different one. But it's a little easier to tell here because I say it's usually what's inside of something, and that's the case here. It's inside of this something squared, and it obviously wouldn't just be x, right? That wouldn't make sense. So it's ln of x. It never is just x. That doesn't do anything. That's just that. Do you see what I mean? I would just replace them with u's, and then you wouldn't have anything different. So ln of x is what it is. All right, we're doing the same thing again. Du here, dx here, u prime here. Ln x derivative of that is 1 over x. Now we get dx on by itself. Dux is pretty much what we get, or x du. Now we go over here, replace ln x with u, divided by 2x, and we replace dx with dux, and then the x and x cancel out. Just because it's 2x and x doesn't mean you can't do anything. You can cancel that out, but you still have a 2, sorry. Now move this up here. I'll just make it a 1/2. You see what I did? I just put it to the side. 1/2 u squared du. But there's something that I left out. How did we get to a 0 and 1 here? Since we switched to u, think about like you met someone that's speaking Spanish, and you changed one part of your conversation to Spanish if you know Spanish, but the other you left in English. That's not going to work, right? We changed this to you, but over here, this is still in English, but we need to make it in Spanish. I don't know, that's a weird analogy, but that's what I thought of. So this is English. We gotta change that too. It's pretty easy to do. It's right over here. Just plug it into what you said as u. So ln of e, 1, ln of 1, 0. Bam. Put that there. Over here. Now, what is the derivative or antiderivative of this? We add 1 to the exponent, 3. Then we do this divided by this. 1/2 divided by 3, 1/6. And you can check your work. 3 times 1/6 is 1/2, and you would subtract an exponent if you went back. So that's how you check your work. Then we go over here. Now all we have to do is plug in. Here's the thing. Now listen up. Remember I said there's a common mistake people make. The mistake is that they switch it back to ln x because they're thinking of one like this. But when you change the bounds, anytime you do that, you don't switch back. So if there's one thing you pay attention to in this video, that's what you should. If you change your bounds, Don't change back to x. That's once again like changing back to English, only part of it, but you have to be all in one thing. So if you changed it back, that would not be good. Okay, that's not what you do. So you just plug in one here, and then so that would give us 1/6 minus, if you plug in 0, 0, 1/6 minus 0, 1/6. All right. What if the substitution is not immediately obvious? So here's another example. I see this right here. Uh, well, the only options are tangent 4x, but that wouldn't change anything. And if we did 4x, that also wouldn't change anything because so what we actually have to do is change this to sine over cosine because tangent equals sine over cosine. A good way to remember that is tusk. I hate trigonometry. Tusk. T equals S over C. Tangent equals sine over cosine. Tusk. So I do that right here. And now we choose U. I don't know. That's not supposed to be U prime, by the way. That's just a 1. Um, U equals, and cosine 4x is what we would end up choosing once again. If you chose sine, you would find out that doesn't work and you would change it. So I'm only doing this already after the fact. For this one, there's not really a specific, well, actually, it's number 2 right here again, because if you do cosine derivative, you get a sine, so you'll assume that will cancel out. And since we have a 4 there, that's also useful, as we'll find out. So anyways, we have du dx, and then the derivative of this is this chain rule, because we did the derivative of just cosine x, that's sine x, but we have to have sine 4x. And then don't forget about doing the chain rule. We also have to do what's in the parentheses and multiply it by it. So 4. And by the way, it's actually negative sign, sorry. Negative sign, and then that 4 just comes, it was over here, but I just put it over here. Review chain rule if you don't remember it. Now we solve for dx, du over that. Now we have to change the bounds as well. We do cosine 4 times pi over 16. That would be root 2 over 2. I'll come back to that in a second. Cosine 4 times 0, which is cosine of 0, which is 1. That's the easy one, right? We know what cosine of 0 is, but we might have not known what cosine of 4 pi over 16 or pi over 4 is. If you didn't know that, I have to say, hopefully you wouldn't get points off. At least usually you shouldn't. You could just leave it as that unsimplified, although that would make your work kind of sloppier at the end because you wouldn't get an actual number. But that's what I would personally do because I personally am weak on the unit circle. But this might just tell you also, just learn the unit circle. But these are our new bounds anyways. So now same process, we plug in, we're using this part. We plug in U right here, switch that out to U. We replace dx with this. So right here, that cancels out. Now we have 1 over 4u. We can separate that to negative 1/4 times 1 over u to make it easier because that part can be changed to ln of absolute value of u plus c plus c. We need a plus c right there. Um, oh, actually not. I don't. Oh, sorry about that. That's a mistake right there. You don't need the plus C because we have these bounds. Sorry about that. Mistake, no plus C. So we have this right here. This 1/4 remains the same even when you take the antiderivative, and then you plug in this here, and that gets a little funky, but we end up doing this is what the answer ends up being, ln 2 over 8 if you do solve this out, which you plug this into here, and then minus plugging that there. All right, this one's a little easier in my opinion. This time I'd set u definitely to be x plus 1 because it's inside of something. But the reason why I'm showing an example like this, you'll see in a second. So same process, du, dx, u prime is 1. Oh, in this case, they just equal each other. Now we plug this in and we get cube root of u times x squared, but then you're like, hey, what do I do? You can't have x and u. Well, we can get rid of that stupid x squared. How? Well, if we know that u equals x plus 1, then x equals u minus 1, which means x squared equals u minus 1 squared. Yes, I know that might seem a little what, but that's what you should do. Anytime you end up with something like this, like, oh, great, I have x and u, either you did the wrong u, but in this case, you didn't do the wrong u. All you have to do is use your u equation to solve for x and then make it the way you want. We want it to be squared, so we square both sides. So now, bye-bye, we replace that with u. It's just like translating, like, let's say this is English, this is Spanish. Oh, how do we get it into Spanish? Because we have to have all Spanish here. Ooh, now we did. So now, here's where it gets kind of stupid. We change this to u to the 1/3 to make it easier. We FOIL this out, and then we distribute to get this. And this is not even doing the antiderivative. This is just getting it to a point where we can do the antiderivative, because we can, just like that. So we do it like that. Now we can do the antiderivative. And that's your answer, and no bounds. So you do need to plus c here. And I didn't finish solving it, or I didn't switch it out to x. You would have to switch back to x. Didn't change the bounds because there are no bounds, so you do switch back to x. No, if you didn't change the bounds or there are no bounds, switch back to x. If you did, then don't switch back to x. There you go. Thanks for watching.